Welcome to AI Paperslop. You know, the YouTube series where we summarize AI and tech papers. And today we're jumping into a paper called S-Agent, which is a spatial tool-use agentic paradigm for continuous multi-view image and video reasoning.
Right, coming out of NTU, Tsinghua University, ByteDance, NWPU, and Repedia. It's a heavy hitter.
It really is. So to give you the zero-fluff summary right up front, current vision language models, or VLMs, they completely fail at continuous 3D world understanding.
Yeah, they really do.
Because they treat video frames as isolated, stateless 2D snapshots, just flat images. So S-Agent fixes this by casting the VLM strictly as a semantic planner.
Exactly. The model stops doing the geometric math itself.
Right. Instead, it actively calls on a hierarchy of spatial tools to extract, 3D metric depth, point clouds, and object grounding.
And crucially, it tracks all this over time, using persistent scene memory and agent memory.
Which is huge. And this framework is training-free, but it massively boosts zero-shot models like GPT 5.4.
But they didn't stop there, which is the best part.
Oh, for sure. They distilled 100,000 reasoning trajectories into this heavily filtered dataset, S300K.
Yeah, to fine-tune a compact 8 billion parameter model, S-Agent 8B, which is now rivaling massive proprietary models.
It's wild. But before we get into the architecture, we really need to look at why current frontier models are struggling so much. The semantic gap.
Right, the semantic gap. When you look at the training data for these massive VLMs, they're trained passively on 2D visual text corpora.
Billions of static images paired with text.
Exactly. They do not have embodied experience in a three-dimensional physical world. So when you prompt a VLM to, say, determine the exact distance between a sofa and a TV...
It's not running a geometric calculation.
No, not at all. It relies on lossy semantic representations.
Which is, essentially probabilistic hallucination.
Exactly. The self-attention mechanism in a transformer is just correlating text tokens with 2D image patches.
Right, so it learns that the token for television often appears spatially near the token for sofa in a flat pixel space.
Yeah, so it just outputs a spatial relationship that sounds plausible, but there's no native inductive bias for three-dimensional Euclidean space.
It doesn't actually understand that the television is like 1.5 meters deep along a z-axis.
Right. It is entirely a token prediction illusion. And this weakness is exponentially magnified with continuous video.
Because standard VLMs process video as disconnected, static frames.
Exactly. The moment the camera pans away from the television, that television ceases to exist in the model's spatial understanding.
It's effectively starting its spatial map from scratch with every single frame. Which makes me think of a Polaroid analogy.
Oh, yeah, the Polaroids.
It's like trying to navigate an unfamiliar living room by rapidly flipping through isolated flat Polaroids of the furniture. You'd be bumping into walls in seconds.
It's a terrible way to build a mental map. Transformers are incredibly good at language routing and semantic logic, but notoriously bad at rigid math.
Right. You wouldn't ask a language model to manually compute a massive floating point matrix multiplication.
Exactly. So why are we asking it to manually compute metric depth from flat RGB arrays?
Which is where S-Agent comes in. It introduces this strict separation of powers, reassigning the VLM as a semantic planner.
Yeah, the VLM is basically promoted to a manager role. Its only job is to evaluate the prompt, look at the state of the environment, and decide what evidence it needs.
So it outputs a text-based tool call, waits for an observation string, and decides what to do next.
Right. It offloads the spatial computation to a strict three-level hierarchy of tools.
Let's break down those tools, because level 1 makes total sense to me. It's your basic 2D foundation, right?
Yep. Open vocabulary detection.
So the planner needs to locate a potted plant. It invokes level 1, feeds it the text string potted plant.
And the tool scans the 2D frame and returns a standard bounding box. X-min, IMAX coordinates on the flat image.
But a 2D bounding box doesn't solve the Polaroid problem. If the camera moves, those pixels are useless. How does it turn that flat crop into something useful?
That's level 2, the 3D lifting tools. This is where we bridge that semantic gap.
Okay, so how does the lift work?
Level 2 takes that 2D bounding box and passes it through monocular depth estimation pipeline.
So instead of just RGB values, it assigns a metric depth value to every single pixel in the crop.
Exactly. And by combining those depth maps with either camera intrinsics from the metadata or just scale priors.
It projects the 2D pixels outward into a 3D frustum.
Yes. It translates the flat image into a dense spatial point cloud with actual X, Y, and Z world coordinates.
Wow. So the planner doesn't just see the word plant anymore. It gets an exact multidimensional array representing the plant's volume in absolute space.
Right. But a point cloud is just raw data. The LLM still can't natively read a massive array of floats.
Which brings us to level 3, the aggregation experts.
Yeah, these are specialized deterministic algorithms. You've got a counting expert, a metric measure expert, a visual orientation expert.
So because level 2 handled the heavy lifting of the 3D projection, level 3 can run hard calculations over the point clouds.
Exactly. Let's put it in practical terms. If you ask, how far is the plant from the sofa?
The VLM doesn't guess.
Right. It asks level 1 to find them, asks level 2 to lift them into 3D point clouds.
And then hands both to the level 3 metric measure expert.
Which calculates the Euclidean distance between their centroids and returns a string. The absolute distance is 1.0 meters.
Or the visual orientation expert, which is super cool. It calculates relative perspectives.
Yeah, it can determine that from the sofa's perspective, the plant is on the left. Or even project the 3D data down into a bird's eye view map of the room.
Okay, wait, I got to push back on this architecture for a second.
Sure.
Because as an engineer, we've had agentic VLMs using external tools and Python APIs for a while now.
Sure.
Models like VDAR or Space Tools, they dynamically construct code to solve spatial queries. So why is S-Agent actually a paradigm shift? Aren't we just plugging a depth estimator into an LLM and hoping it routes correctly?
If S-Agent only used these tools frame by frame, you'd be absolutely right. It would just be another API wrapper. The limitation of models like VDAR is that those spatial tools are useless over a continuous video if the agent forgets what it measured 2 seconds ago.
Right. If a bounding box moves off screen, the 3D calculation is gone.
Exactly. The true innovation here, what creates actual statefulness, is S-Agent's dual temporal memory system.
The memory mechanisms, yes. Let's unpack this, because we need to stop thinking about the VLM as someone looking at Polaroids and start thinking about it as like an amnesiac detective.
I like that.
A standard VLM forgets everything when it blinks. But S-Agent gives the detective 2 things: a physical corkboard, which is scene memory, and a detailed notebook, which is agent memory.
Perfect analogy.
So how is the scene memory maintaining the physical reality of the room?
Scene memory is essentially a continuously updating vector database of physical objects. It tracks grounded entities across changing frames.
Preserving object identity.
Right, and actively suppressing duplicate evidence using 3D non-maximum suppression, or NMS.
Let's define the mechanics of that NMS process. Because in 2D object detection, NMS just deletes overlapping bounding boxes, so you don't count the same card twice.
Yeah, but doing that across a moving video is much harder.
Right.
So it calculates the intersection over union, the IOU, but in 3D coordinate space.
Okay, so if level 1 detects a plant in frame 1, scene memory stores its 3D centroid.
Yep. And if the camera pans in frame 2 and the tool fires again on a plant, scene memory compares the new 3D coordinates against its database.
If it's looking at absolute metric space, not just 2D pixel overlap.
Exactly. It calculates a high 3D IOU and merges the data. It realizes, hey, this is the same plant I mapped earlier.
Updating the state rather than duplicating it. That's the corkboard. But the detective also needs the notebook. Agent memory.
Right. While scene memory tracks the physical room, agent memory tracks the cognitive reasoning.
It's a dynamic scratch pad for the conversation history. It logs the thought tag, the specific tool call syntax, and the raw observation string that comes back.
Which is vital for iterative refinement. Say the planner needs to find a small object, like keys. It invokes the detection tool, but the tool returns an empty observation.
It failed to find the bounding box.
Right. Because of agent memory, the semantic planner doesn't just loop endlessly. It reads the notebook, sees the failure, and wraps.
Like saying, the default threshold missed it, I'll invoke the tool again with a lower confidence threshold.
Exactly. Or calling a different tool to zoom in. It allows for multi-step recovery.
Which makes total sense. And using a frontier model like GPT 5.4 as the planner makes it phenomenally capable. But
deployment constraints.
Exactly. You cannot run a massive proprietary model constantly pinging servers while spinning up 10 visual experts in a real-time robotic loop. The token overhead alone.
It's paralyzing. And the authors knew this, which leads to the S300K dataset and their distillation pipeline.
They wanted to prove this agentic behavior could be distilled into a compact open-weight model, teaching a smaller model how to think like a semantic planner.
Right. And their pipeline for generating that data is brilliant. They started with 100,000 spatial reasoning questions from the Sensinova SI800K dataset.
Highly diverse, open-ended spatial queries.
Yeah, and they ran the zero-shot S-Agent framework over them using GPT 5.4. letting the massive model generate the ideal tool-use trajectories.
But just generating them isn't enough. You have to be ruthless with filtering.
Oh, absolutely. If you fine-tune on flawed reasoning, the small model will confidently hallucinate.
So for numeric questions like predicting the exact distance between two objects, they didn't just check for an exact match, they used mean relative accuracy, MRA.
Right.
Let's explain MRA for a second. It measures the absolute difference between the predicted value and the ground truth, relative to the size of the ground truth.
Exactly. So if the true distance is 1.0 meters and the agent predicts 1.1 meters, the relative error is small. The MRA score stays high.
But if it predicts 10 meters, massive penalty.
Yeah. Any trajectory with an MRA lower than 0.6 was entirely discarded. And for free-form text, they required exact substring matches.
Which eliminated nearly half the data. Out of 100,000, only 51,596 mathematically validated trajectories remained.
But here's the really clever part. They didn't just dump those 50,000 end-to-end examples into the fine-tuning run. They decomposed them.
This is a huge takeaway for anyone building SFT datasets. They break each trajectory down into 3 distinct types of samples.
Right. First, the final answer samples, mapping observations to the conclusion.
Second, the turn-level planner samples, teaching the step-by-step logic, how to output a thought tag and generate tool call syntax.
And third, the tool-specific samples. So by decomposing those 50,000 runs, they generated 292,391 supervised fine-tuning samples, S300K.
And decomposition is so critical because it forces the weights to prioritize reasoning over rote memorization.
Exactly. If you only train on the final mapping, the model learns a shortcut. It tries to memorize relationships instead of learning how to invoke the depth estimator.
It teaches the cognitive pacing of a manager. So for hardware, they fine-tuned the open-weight Qwen3 VL8B instruct model,
using 8 B200 GPUs.
But there's a fascinating detail here. They explicitly did not use tool calling frequency as a filter.
Which seems counterintuitive. You'd think a tool use agent needs examples where it invoked multiple tools.
Right. But by focusing purely on final answer correctness, they allowed the model to learn discretion.
Exactly. It learns efficiency. S-Agent 8B realizes that for simple questions like, is the sky blue, it doesn't need to waste compute calling a metric depth expert.
It only outputs tool call syntax when the geometric complexity demands it. It's so smart.
Yeah, it is.
So we've got the architecture, the memory, the S300K distillation. The big question, what do the benchmarks look like?
The benchmarks completely validate the paradigm. Let's look at the training-free zero-shot gains first. Wrapping base GPT 5.4 in the S-Agent framework without altering weights boosted it on View Spatial Bench by an average of 14.4%.
That's great, but wait, I have to push back on one specific stat. The paper claims a massive 20.5% gain on the PSSRD split.
Yeah, the person perspective scene simulation relative direction.
Right, so a prompt like, you're facing the TV, turn 90 degrees left, what object is 2 meters in front of you? A 20% gain just from attaching tools. Is base GPT 5.4 really that bad at relative direction?
It genuinely is. Remember the semantic gap. A VLM cannot mentally simulate 3D rotation from a 2D image because it has no coordinate space.
It relies entirely on text priors.
Exactly. The 20.5% jump isn't a rigged benchmark. The visual orientation expert uses the absolute 3D data from level 2 to deterministically compute the direction.
He replaces a guess with a measurement. But what about the distilled S-Agent AB? How does it perform given the compute disparity?
On MMSI Bench, S-Agent AP surpassed its own base model by up to 10.5%. And remarkably, it boosted zero-shot performance over Gemini 3 Pro by up to 1.2%.
Wow. Over Gemini 3 Pro. If you're deploying a spatial agent in production, that changes everything.
Oh, absolutely.
Don't have to pay massive API costs per token. You can run an 8B model locally on a single node and get superior geometric reasoning.
And on the RevESI benchmark, it ranks second overall, outperforming all open source baselines and spatially specialized models like Cambrian S and VST SFT.
Specifically dominating in relative direction and route planning.
Yeah, and route planning is the ultimate validation of the memory systems.
Because you can't plan a route looking at a single Polaroid. The scene memory is actively maintaining coordinates of off-screen obstacles, while agent memory tracks the movements.
Exactly. Accumulating stateful evidence over time. It proves that breaking down a continuous task into managed subtasks governed by memory is way more effective than just scaling up parameters.
Which brings us to the real-world implications here. We've talked about benchmarks, but if an 8B model can achieve state-of-the-art spatial intelligence by offloading its geometry, what happens when we put this in embodied robotics?
That's the horizon line. The holy grail right now is semantic slam. Simultaneous localization and mapping combined with deep semantic understanding.
Current autonomous systems struggle so much with persistent spatial memory in dynamic environments.
They really do.
So imagine a humanoid robot in a warehouse or a home, not just for a 10-second clip, but running continuously for weeks. Its scene memory wouldn't just track a bounding box, it would reconstruct the metric reality of its physical world.
Updating in real time. Resolving conflicts through 3D IOU.
Remembering exactly where every object was based on hard geometric coordinates, not fuzzy text associations.
It bridges the gap between a machine recognizing pixels and a machine actually knowing its environment.
And localizing that intelligence via an 8D model is a massive leap for physical robots. How drastically will autonomous systems change when they stop treating reality like a stateless flipbook and start interacting with a persistent, measurable coordinate space?
It's going to change everything.
Something to think about for sure. I highly recommend you dig into the paper's specific SFT decomposition methodology. Look at how they used mean relative accuracy to filter S300K and think about how you might distill these multi-step agentic loops into your own pipelines, because the era of asking a language model to do 3D math is over. The era of the semantic planner is here. Thanks for tuning into this deep dive on AI paper slop, and we'll catch you next time.